Okay, welcome back, guys, to the show that never ends. It's a Emerson, Lake and Palmer song. It's great. You should look it up. Anyway, here we go. Organic compounds that contain oxygen and sulfur, which is a bunch of them. Things are pretty simple when it's just carbon and hydrogen. When we start adding heteroatoms like oxygen, sulfur, and nitrogen, things start to get pretty darn interesting. So let's go through the business. We're going to deal mostly with alcohols, ethers, and then thiols. And you know how we do this. We talk about naming them. We talk about them from a biological point of view. We talk about reactions. And we talk about properties. So let's start our business. 3 families of compounds that contain a carbon atom that is single bonded to oxygen and sulfur. They are alcohols, which contain a hydroxyl group, which is an OH attached to a carbon. An ether, which has carbon chain single bonded to an oxygen atom and then a carbon chain. And in general, R is just an alkyl group, which is just like CH3, CH2, blah, 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 blah. An ether has 2 attached to that oxygen with a pair of lone electron pairs on the oxygen. Alcohols are similar, but they just have an H attached. 2 examples are ethanol and diethyl ether. These are 2 pretty common chemicals used a lot for lots of different things. As we'll find out later, this is an anesthetic. Diethyl ether is an anesthetic, one of the first ones. And well, I guess you could think of ethanol as an anesthetic too if you chose to. Okay. And then there are thiols as well. That's the third category here, which act very much like an alcohol because they look very much like an alcohol. After all, sulfur is right below oxygen on the periodic table, group 6A, so they have similar chemical and physical properties. Let's dive straight in to naming of alcohols. So whenever we're dealing with alcohols and we want to name them correctly, we do the same thing that we always do. Parent compound identification. The parent has to contain the hydroxyl group, and then you change the ending. Instead of pentane or ane, you change it to -al. So, step 2, how do you do your numbering? You number the carbons in the parent chain to give that hydroxyl group its lowest number. And then you apply all those other rules. That's why if you crank hard on naming rules in the early sets, the naming rules on the other compounds is often very similar. So you just do this sort of same business rather than have to memorize brand new things. And when we have a cyclic alcohol, we always start the counting as 1 where the OH group is. And so you never have to write in the 1. It's redundant. And then you write the entire name as a single word, identifying the number in each substituent and the hydroxyl group, unless it's on carbon 1. You use hyphens to separate the numbers and use hyphens to separate the numbers from the prefixes, commas to separate the numbers. Prefixes are in alphabetical order. And an aromatic alcohol, we like to call that phenol. All right, examples. IUPAC name of this guy. What's our first step? Find the longest carbon chain containing the carbon bonded to the OH. And the longest carbon chain is here. And I think it's clear that we would 1, 2, 3 versus 1, 2, 3, 4. So we're going to start the counting here. And since there's 1, 2, 3, 4, 5, 6, that means this is a 6 carbon chain. So it's going to be a hexane, right? But we're going to change the hexane, 6 carbons, the ane to the anol. Change the E to OL, so hexanol. All right. Step 2, number it to give the OH group the lowest number. That's why the 1 is over here, as we talked about before. And then apply the other rules. The other rules are carbon 5 has the methyl group, which gives us 5-methyl. You're doing this on your own, right? You already have this down. 3-hexanol. 5-methyl, 3-hexanol. Good. What if we have a ring structure for an alcohol? The OH is automatically on carbon 1, and so you'll do the counting to the smallest number for the substituents, 3. So what do we got here? Well, we've got 3-methyl, and look, that's a circle, so don't forget the cyclo. So 3-methyl cyclohexanol. That's it. It's not too bad. Okay, so there's 2 different ways that you could do a problem like this one. Which of the following is the condensed structural formula of 3-pentanol? You could, of course, name that and see if it matches up. Name that. See if it matches up. Name that. See if it matches up. Or you can draw this from the name and see which one matches up. So let's try that one. 3-pentanol. 3-pentanol says pentane. So 1, 2, 3, 4, 5. And I'm not putting all the hydrogens in right now because I remember that this is 3-ol, which means the OH is on carbon 3. If we decide that this is carbon 1, this is carbon 2, so it'll have its 2 hydrogens. This one has an OH attached, and this has 2, and this has 3. So that's 3-pentanol. Any of these look like it? How about that one? There you go. So what would this be? This would be 1, 2, 3. That's just propanol, or 1-propanol. That looks like 1 dash. And this is 1, 2, 3, 4, 5. So that's 1-pentanol. Not 3-pentanol, because the OH is on the first carbon. Okay. So clearly A is the right answer here. Moving on. Simple alcohols, which are usually smaller, have common names that get used all the time. And the way we do common names is we name all the carbons as a single alkyl group, like methyl, ethyl, propyl, etc. And then you add the word alcohol with a space in between. So that's the propyl group. And we know the OH is attached on the end. So we add alcohol, and this becomes propyl alcohol. Pretty simple. All right, so IUPAC names. Clearly there's no common name that can be used here because these aren't simple alcohols. IUPAC name says longest chain. That includes the alcohol group. Hey, where's the carbon start here? Is this a carbon? Is this a carbon? And the answer is no and no. This is a carbon, that's a carbon, that, and that. So the longest chain is 1, 2, 3, 4. So that makes this a butanol. Where is the hydroxyl group? It's on carbon 1. Okay, so 1-butanol. Got 2-methyl, 4-chloro. Chloro comes before methyl. So if this is a 2-methyl, this is a 4-chloro, put them all together. 4-chloro, 2-methyl, 1-butanol. Not too bad, not too bad. Okay, so if you've got a ring, the ring is the parent for this guy, and that's obviously carbon number 1. That's going to be a smaller number, so we'll definitely do the counting like that. This is a 2-ethyl, and this is a 4-isopropyl, and the hierarchy goes E before I. So what do we got here? This is a 5-carbon ring. E comes before I, so we're talking 2-ethyl, right? Followed by 4-isopropyl. So that's where they're hanging off the cyclopentanol. 2-ethyl, 4-isopropyl. Well, that's about as easy as it gets. Very nice. How many carbons are on there? That's maybe the hardest thing for you guys to remember. 1, 2, 3, 4, 5. So the IUPAC name says 1, 2, 3, 4, 5 carbons. One pentanol lets us know that the hydroxyl group is on carbon 1. Now the carbon, the common name, I mean, is 5 carbons is a pentyl group, so you would just write pentyl alcohol. That's it. Not too bad. All right, so now we're going to go line formula from the name. That's always interesting and not too bad. Hepta means 7 carbons, right? So line formula says 1, 2, 3, 4, 5, 6, 7. And if there are 3, means the OH is on carbon 3. So if we decide that the first one is 1, 2, OH, that's it. That's the line formula for 3-heptanol. Doesn't take long, not too bad. Butyl alcohol. Butyl group is 4 carbons. So 1, 2, 3, 4. And There's nothing special, so the alcohol's off the last carbon, OH. That's it. Cyclohexanol is 1, 2, 3, 4, 5, 6 with an OH anywhere you want it. That's carbon 1. 3-ethyl means 1, 2 off the ethyl. Man, that's not bad. You can do that. I know you can do that. Let's keep going. Okay, the common name is alcohol is at the end. And what is that thing? That's a cyclobutyl group. So cyclobutyl alcohol is the common name. Cyclobutanol would be the IUPAC name. Next. One carbon is a methyl group, so this is methanol. And it is very useful and used all the time, but it's also toxic in the body due to oxidation products that are formed in the liver, and we'll talk about that later. Ethanol, some of you may have heard of this stuff. Alcoholic beverages formed from fermentation of carbohydrate chains. And 2-propanol is much more commonly known as isopropyl alcohol, or isopropanol, is what's mostly there in rubbing alcohol. And this is one of the reagents that is running out with this COVID crisis because it's a sterilizer and it's being used to in great amounts. Structure and properties now of alcohols. That hydroxyl group is the thing that makes an alcohol an alcohol. So because they have that OH group, they get classified and categorized by the number of carbon atoms or alkyl groups that are bonded. That is the alcohol group. We look at this carbon and we decide how many carbons are attached to it. The answer is 1, and that makes this a primary alcohol. Primary alcohol has an OH group on a carbon bonded only to 1 carbon atom. Okay, so that's a primary. 1 alkyl group is attached. That makes it. Now, if you have 2 alkyl groups attached, I think it's probably pretty clear what that's going to be. Secondary alcohol, OH group onto a carbon bonded only to 2 carbon atoms. Okay, so if that is the alcohol, a lot of people circle that as the alcohol, and that's not right. That's a hydroxyl group. An alcohol is the hydroxyl group bonded to the carbon, and that carbon is where we're deciding is whether it's secondary, primary. And since it has 2 carbons attached, that makes it secondary. And as you can see, this is the alcohol. That's the carbon in question. 1, 2, 3 carbons attached. That makes it a tertiary alcohol. 3 carbon atoms attached. So if we looked at this big old molecule here, find the alcohols and then classify them as primary, secondary, or tertiary. All right, so there's your carbon, and there's the alcohol. So that carbon has an OH group attached. It has to have an H and an H and a C, right? And since there's one carbon, there's the one, this carbon is primary. Any other primaries? Sure, anything that's on the end of a chain, because it's got a hydrogen, an OH, that's the alcohol, that's the carbon, so that's another primary carbon. There's two more alcohols. That carbon is bonded to that OH, so that's the alcohol. That's a carbon, that's a carbon. What else is attached to this carbon right here? 1, 2, 3, well, it's got to have an H on it, right? Two carbons, that makes it a secondary alcohol. What about this guy? That's the alcohol. There's a carbon, and a carbon, and an OH. That's the 4 bonds. So that carbon right there is a tertiary carbon. That's how you have to think of it. It's not bad, but it also points out why we needed to know and keep track of the number of bonds that carbon makes in an organic molecule, and also adding on the hydrogens. Cool. No, there's no quaternary alcohol, because if you had a carbon with 4 carbons attached, for it to be an alcohol, it has to have an OH, and that's 5 bonds. Can't have 5 bonds. On carbon, too many electrons. Good. All right, so let's do another judge. Secondary alcohol. Let's do this fast, okay? There's the alcohol. 1, 2, secondary. There's the alcohol. 1, hydrogen, primary. There's the alcohol. 1, 2, 3 carbons attached, that's tertiary. That's like printing your own money. That's how easy that is. Just practice up and be real good at it. Structure and property. An alcohol contains an O atom with a tetrahedral arrangement or geometry. Why? Because if you remember with your shapes of molecules, that center oxygen right there has one place where electrons can be found, 2 places where electrons can be found, 3 places, and 4 places. 4 places with electrons equals tetrahedral shape, not shape, tetrahedral geometry. Lone pairs are invisible. They're there, but you can't see them. And so that leaves you with a bent shape. This is an important thing. That's a Chem 111 skill. So look back in your book and get better and practice up on your shapes of molecule stuff. So it's a bent shape, and the bond angle actually is less than 109.5 because these big negative lone pairs will squeeze these together. So it's maybe more like 104.5. But in any case, it's a bent shape. Because it's a bent shape and there are 2 polar bonds, partial positive is over here, partial negative is up here, and therefore it has a net dipole. And it's a polar molecule. That's how we want to think of it. It's a polar molecule, as well as polar bonds. Since the H is directly bonded to an O atom, you can have intermolecular hydrogen bond forces. Remember, this is a strong IMF. And here's where it happens. There's the lone pair on the oxygen, and that's partially negative. And the hydrogen over here on an adjacent alcohol is partially positive. That is an attractive force there, which keeps these guys holding on to each other. That's why it's a strong IMF. Intermolecular force helping them hold on to each other. If they hold on, that means they don't want to let go, and that affects structure and properties. So, stronger intermolecular forces than alkanes, which are just dispersion. Dispersion forces. And we'll talk about ethers later. Alkenes are also mostly dispersion forces as well. And ethers, as we'll find out, have no H bonding. So alcohols, very strong IMFs. And what does that lead to? They have higher boiling and melting points. Okay, so why is that? Well, remember, an intermolecular force is like a handshake. If it's a real weak handshake, then the two people aren't going to be connected very easily. But if it's a real strong handshake with two hands and then a hug and then wrapping a leg around and intertwining, then it's real hard to get them apart. And so therefore, if you have higher intermolecular forces, it takes more energy to get you from the liquid phase where you're connected into the gas phase where you're not. So butane and butanol, very similar looking molecules, 60 grams per mole, 58 grams per mole. They're very much similar size, and maybe their melting points aren't that much different. You got to be a little bit warmer to get frozen propanol into the liquid phase, but look at those boiling points. Butane boils at just below freezing water. And the boiling point for propanol is almost similar to the boiling point for water, just below that. So it takes a whole lot more energy to get these propanols up into the gas phase. That's what we're talking about with intermolecular forces. That's because the intermolecular forces for butane are just dispersion forces, whereas for propanol, you've got dispersion, you've got dipole-dipole, because these are dipolar molecules, and you've got that H bonding. And therefore, much higher, much stronger intermolecular forces, much more energy required to jump that guy from the liquid phase into the gas phase. Because an alcohol is an organic molecule, it is soluble in organic solvents. That's going to be the case for all of these organic molecules. They're soluble in organic. The big question is whether they're soluble in water. The low molecular weight alcohols basically 4 to 5 carbons are soluble in water, meaning they will dissolve. But the higher 6 carbons and up are not soluble. They're just too greasy. They're just too much nonpolar. And so they will not solubilize, will not dissolve in water. So 2 carbons in the chain. This is ethanol. Pretty clear that when somebody has a vodka tonic, they're having alcohol added with water, and there's not 2 different layers. So this is going to be soluble in water, but big, long, non-polar part, this is octanol because it's got 8. This is going to be insoluble in water. However, both are soluble in organic solvents. That's an important thing to remember. Alrighty. Now once we've gotten through names and properties, now let's start talking about reactions. Well, one of the reactions that you're obviously familiar with is combustion. React with oxygen to form carbon dioxide, water, and energy, and alcohols do that readily. Don't forget to balance. You know how to do that. However, there's a set of different kinds of reactions that we have to be ready to anticipate, describe, and predict. Dehydration. You remember hydration, where we added water to an alkene to get an alcohol? Well, this is the reverse of that. Dehydration. To get hydrated, you add water. If you're dehydrated, that means you've lost too much water. So dehydration is the loss of water from any starting material, and there's a loss of an H from one carbon and an OH from an adjacent carbon. Doesn't happen on the same carbon, it's adjacent. And then you end up forming water, H2O or HOH. This occurs when an alcohol is treated with some strong acid like sulfuric acid, and it forms an alkene product, forms a double bond. So this water jumps off here, we form the double bond, and water is one of the products. Don't forget that when you dehydrate an alcohol, water is a product as well as an alkene. And this is an example of an elimination reaction in which parts of the starting material are lost or removed and a multiple bond gets formed. This happens a lot. Here's some examples. Pretty simple. The water leaves this ethanol, this H, that one carbon bond, and that other H aren't changed at all. When we remove the water, what's left is a double bond between the two carbons. Let's try this again. the rest of this stays the same, doesn't change. There's no reaction going on there. I think I messed it up, but that's all right. The water leaves, and you have a double bond. I messed that up. That's ugly. 1, 2, 3, 4, 5, 6 plus water. We've got the double bond down here. Okay? Dehydration and hydration are just reverse processes. When we have dehydration, you start with the alcohol and end up with an alkene plus water. And hydration takes the alkene and with the dilute acid adds water on to make an alcohol. So the alcohol gets dehydrated by heating, adding a lot of acid, and you make the double bond plus water. And here, if we go the opposite direction, we add water to this double bond, we'll make the alcohol. If you remember Markovnikov, where there was symmetrical and asymmetrical, same kind of thing is possible here. These are symmetric because there's a plane of symmetry. It's exactly the same on both sides. But you can also have asymmetric alcohols. No plane of symmetry here. If we drew a line right through the alcohol part and then looked at the other side, it wouldn't be a mirror image, right? This only has a CH3. This has a CH2 and a CH3. And clearly this has a methyl group on this side and it doesn't have a matching methyl group on the other side. So those are examples of asymmetric alcohols. And that's going to be one of your job, looking closely at the molecules to see the kinds of reactions that could happen. And when we're dealing with dehydration of an asymmetric alcohol, remember, dehydration is carbon, carbon, OH, H. And what happens is the water leaves, or the water leaves. The question is, which one? But we have to make sure that we're looking at the alcohol and then a carbon on with a hydrogen on an adjacent carbon. So we've got an asymmetric alcohol right here. There's two different possibilities, right? Two different. Remember, this carbon also has an H attached, and so does this. So we could take the OH from this carbon and the H from this carbon, at which point the double bond is in between, and there's where the water is left. That's one path. Here's the second path. This carbon also is attached, and it's got 3 hydrogens on it. And so you could take these two on path B and would make the double bond on the end in the water. Now, whenever we have this, and we have a double bond in the middle of a compound, a middle of a carbon chain, you could make the carbon go down and hydrogen go up. So it could be actually cis-trans isomerism that goes on with this. But that's still not answering the original question, which is, which path is preferred? Because one is preferred over the other. So how would you decide? You remember in Markovnikov, we said that the rich get richer, that like gathers with like, and so whenever we were adding the H and the OH, that the H's went with the other H's, with the carbon had the more hydrogens attached. So what's the preference here? Take a guess, see what you think. You ready? Let's find out. Zaitsev is a different Russian who did some work on this. And what he found with all of his work was that the major product has the most alkyl groups bonded to the carbon-carbon double bond. In other words, the most substituted alkene, or in other words, H will leave the carbon atom with the least number of hydrogens attached. Another way of saying that, the hydrogen poor get poorer. If the rich get richer when you're adding, then the poor get poorer when you're taking away. Sounds like trickle down economics. I don't want to talk about it anymore because this is chemistry class, but that's the idea. So if that's path A, we had a choice here between this carbon, which had 3 hydrogens attached, versus this carbon, which had 2 hydrogens attached. Because if you remember, the other choice was this carbon with 3 hydrogens attached and this carbon with 2 hydrogens attached. And since the major product has the most alkyl groups bonded, which means the H will leave the carbon atom with the least number of hydrogens, this path A is preferred. Got it? Okay, so let's put it into action. Guys, there is no doubt about it. This is the challenging part to this class. You can identify that as an alcohol. You might even be able to name it. But when you're doing organic chemistry, your job is to, number 1, look at the compound. Identify what kind of compound it is. Look at the reagent. Understand what kind of reaction will occur with that kind of reagent, and then have all the Markovnikov and Zaitsev major product, minor product, rich get richer, poor get poorer thought process in your head as well. So how do we think about this? Well, we've got this carbon, 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 carbon. This carbon has 3 hydrogens attached, right? It's always good to be able to put those hydrogens in. Why do you think we had you do that in quiz 1 and earlier work? It's important to be able to decide whenever hydrogens are leaving, you have to know how many hydrogens are there. This carbon does not have any hydrogens attached, but that's the alcohol. So, since these are the same, reaction can go with either one of these. The question is, we're removing the hydroxyl group, right? But which hydrogen is going to leave? Let's do a different color here. So it's either going to take this and this, or this and that. And since the poor get poorer, that means that's the hydrogen that leaves, right? Because this has 3 H's, this only has 2 H's. Okay, so that means, let's get a third color. That means these guys leave and a double bond gets formed right there. So which one of these corresponds to that? Well, that's not an adjacent carbon and that's not an adjacent carbon, so that couldn't happen. It was either going to be between A and B, and since we decided the double bond was going to happen here on the ring, that's the major product. If we took the hydrogen off of this carbon up here, that would be the other, the product that would form. Got it? Oxidation is another kind of reaction that goes on. Reactions in organic chemistry are definitely a challenge. But if you practice them like enough, oxygen, right? Well, you'll recognize increase the number of CO bonds. Moving on. Decrease the number of CH bonds. You have a net loss of hydrogen. And by the way, I should go back. The reality is each of those possibilities in the previous reaction should also have a water attached as well. Not attached, but added, because water is formed. It's removed. Okay. So here's an alcohol. If oxidation occurs, you're going to increase the number of CO bonds. There's 1 CO bond right now. Here, there are 2 CO bonds, so you've increased them. You had a CH, you lost it. So the symbol O indicates an oxidation reagent, something that's highly oxidizing. And potassium dichromate is a very common one that's used. Primary alcohols first oxidize to aldehydes by replacing one of the carbon-hydrogen bonds with a carbon-oxygen bond and make that double bond, that carbonyl group. And then aldehydes, if you have a strong enough oxidizer, will further oxidize to make carboxylic acids, replacing another CH with another CO. So if we start with ethanol, and we have a mild oxidant, you will get rid of one of the CH bonds and make a CO double bond, and that's an aldehyde. And then if you keep reacting it, you're going to make the carboxylic acid. So primary alcohols, if you have a mild oxidant, you only go to the aldehyde. And then if you have a strong oxidant, you'll get all the way to the carboxylic acid. Secondary alcohols make something different. They make ketones. It's the first time that we've looked at ketones as a functional group in a while. Hopefully you'll remember what they look like after we show some. So here's a secondary alcohol with two R groups attached. You'll get rid of the one CH bond and make the CO double bond, and that's what a ketone is. So 2-propanol, or isopropyl alcohol, oxidizes to make acetone. Tertiary alcohols, because they have no H atoms, they cannot be oxidized. So because there's no CH bond to oxidize, there'll be no reaction here. Sometimes you throw stuff together and no reaction occurs. That happens all the time. Examples. Practice. Okay, let's try one. Well, first we have to identify what kind of alcohol this is. There's a C, there's a C, there's a C. And because that's 1, 2, 3 bonds, that's an H. So 2 carbons attached. That's a secondary alcohol. What happens when we oxidize a secondary alcohol? We make a ketone. We get rid of ACH and we make a CO. 1, 2, 3, 4, 5. We make a ketone. This guy is definitely a primary alcohol. So we'll first make the aldehyde. One, 2, 3 carbons. And then if we further react with the oxidant, we'll make the carboxylic acid. 1, 2, 3. Ignore that line. Carbon, carbon, carbon. 3 carbons. Okay, let's decide on this guy. That carbon has a carbon attached, a carbon attached, a carbon attached. It's a tertiary alcohol. NR, no reaction. Nothing to oxidize. No hydrogen attached to that carbon. Okay. So as we said, tertiary alcohol, no reaction. Whoops, not no reaction. That's the answer, no reaction, because it will not undergo an oxidation. It can't. All right, let's talk a little bit about ethanol metabolism. It's sort of interesting. When ethanol, or grain alcohol, is consumed, it's quickly absorbed in the stomach and the small intestines and eventually makes its way to the liver. When in the liver, there are 2 different enzymes, alcohol dehydrogenase and aldehyde dehydrogenase, act as oxidizing reagents and react the ethanol. The ethanol reacts to make acetaldehyde, an aldehyde, and then reacts again to make acetic acid. Okay, this is what happens in the liver. Now, if you drink more ethanol than the alcohol and aldehyde dehydrogenases can handle, you have a buildup of the acetaldehyde. And if that happens, that's a problem because it's toxic. And that's why drinking to excess gets you in big trouble. Now, when we have methanol, it's similar because after all, it's a small organic molecule. So of course it's going to act similar. Methanol is sometimes called wood alcohol. it gets oxidized into formaldehyde and then formic acid, same enzymes. But both of these are extremely toxic. Consumption leads to decreased blood pH, blindness, and death. And this is an issue whenever we're talking about moonshine. Okay? Because what is moonshine? Well, moonshine is whenever somebody makes their own alcohol in their own stills and then try to sell it. And the government likes to get involved. Why does the government get involved? Two reasons. One, the government likes its cut. So it would like to keep track of what you're making and tax you and get some money off you. But it also needs to check and make sure, because whenever you do a not so good job of distilling your material that you make, you can often get too much methanol in with your ethanol in your moonshine. And if that happens, you can't really tell. And very, very tragic, toxic results can happen. Okay, moving on, moving forward. Now we're going to move to a different oxygen-containing organic molecule, and these are called ethers. An ether have two alkyl groups bonded to that O. And they can be the same group or they can be different. Doesn't matter. Right? That's two ethyl groups. This is a methyl and an ethyl. So it's different, but they're still ethers. Ether is very similar in shape and arrangement. We've got 4 different places where electrons are found. So it's a tetrahedral geometry. But because the lone pairs, you can't see them. See, I drew them in, but you couldn't see them. That's a bent shape. 104.5 angle. Don't worry about the angle. It's a bent shape. And because of that, ethers have polar bonds and they're polar molecules. So let's do some nomenclature. Simple ethers are usually assigned just common names. And the way you do that is real simple. You name both alkyl groups bonded to the O, put them in alphabetically, and then say the word ether at the end. Bing-a-bang-a-boom. This is a methyl. This is an ethyl. So it's ethyl, methyl, ether. Goodness gracious, can't get any easier than that, right? This is an ethyl, and this is an ethyl. So we'll call this diethyl ether. Lemon squeezy, easy peasy. What about that guy? Well, they're two different, right? This is a phenyl group, and this is a methyl group. And M comes before P, LMNOP. So we're going to call this methyl phenyl ether. Good. Pardon me. So those were simple. Now we're going to have some more complex, which means you have to have some sort of IUPAC organized way of naming them. So this is how we work it. We find the longer alkyl group, name it as a hydrocarbon chain, octyl, hexyl, pentyl, something like that. And then the shorter group that contains the oxygen is called an alkoxy group, RO, and it acts as if it's a substituent bonded to the longer chain. So CH3O bonded to the longer chain is considered a methoxy group, and CH3CH2O bonded to some longer chain is considered an F-oxy group. All right. So if we number the longer chain, knowing that this is 3 carbons, so it's a propane, and this is a methoxy group because it's the smaller. And we decided that it gives the lowest number when we count here with the methoxy attached to this carbon. We call this 1-methoxy propane. That's the IUPAC system. The common name would be methyl propyl ether. And I sort of like the common name if you can use it because 1, reminds you that it actually is an ether, and 2, these are easy to add. But there's lots of times when we don't have simple ethers, and so we have no choice. If you see methoxy or an oxy, that means it's an ether. Or if it says ether, that means it's an ether. Okay, let's try another one. IUPAC name for that first one, the methoxy group is smaller. 1, 2, 3, 4, 5. So that's definitely going to be a pentane. So 1-methoxy pentane. Common name for that guy would have to be methyl pentyl ether. Okay, but I hope you see that because this has a branch off of it, that there's no way that we can use the common name. So instead we have to count the branch, the longest branch. 1, 2, 3, 4, 5. So that's a pentane. And this is a 1, 2, 3. So that's a propoxy group, and it attaches on carbon 2. So that's why we would call this 2-propoxy pentane. All right, that's the IUPAC naming process for ethers. Another example for naming. Okay, 1, 2, 3, 4, 5. So that's a cyclopentyl group. And this is 1, 2, 3, 4. So that's a butyl group. Butyl comes before cyclopentyl, so butyl cyclopentyl ether. Nice job. Good job. Moving on. All right, so condensed structural formula from the name. So 1-ethoxy looks like this, CH3, CH2O, and propane looks like this, CH3, CH2, CH3. The 1 says it attaches on the end. So how would you attach that on the end? CH3, CH2, CH2O, CH3, whoops, CH2, CH3. Carbon 1. Not too shabby. Butyl, ethyl, ether. Butyl group is 4 carbons, ethyl is 2 carbons. So CH3, CH2, CH2, CH2O, and then the ethyl on the other side. Man, when we go from name to structure, it goes fast, especially if you know what you're doing. 2-methoxybutane, so that's a 4-carbon chain, and a methoxy group, which is a CH3O, is off carbon 2. So let's draw our carbon, 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 carbon chain. OCH3 is off of the 2 carbon, and then we stick the hydrogens on the rest of the carbons. 1, 2, 3 bonds, that needs 1 hydrogen. 1, 2, that needs 2. 1, so that needs 3. That's it. Not too bad. Moving on. Physical properties of ethers. They have 2 polar bonds and a bent shape, so therefore it has a net dipole. And we consider it a polar molecule because it's got one side that has a partial negative and one side that has a partial positive. Because of the fact that the ether, even though it is polar, does not have a hydrogen directly bonded to an O. So ether does not form intermolecular hydrogen bonds. There's just no hydrogen there. So what does that mean? It's a polar molecule, so dipole-dipole forces for intermolecular forces are possible, but no hydrogen bonding. So because it's polar, which means dipole, dipole, as well as dispersion. Right? Notice how I'm doing this. I'm looking at the molecule. I'm deciding what its shape is and whether it's polar or not. Then that allows me to figure out what the intermolecular forces are. And that allows me to then look at properties like boiling point and melting point. So stronger intermolecular forces than nonpolar alkanes, which only have dispersion forces. But because alcohols have H bonding, IMFs, they're weaker intermolecular forces, right? So therefore, the boiling point should be in between. So they're higher melting points than the hydrocarbons because they have more ways to hold on to each other to keep from going into the gas phase or the liquid phase, but lower melting points and boiling points than alcohols because they're not holding on as tight. And there's some evidence for it. Very similar sized and shape, and I mean, they look very similar, don't they? But butane, because it's just an alkane, only has London dispersion forces. Methyl ethyl ether has dispersion and dipole-dipole, and then propanol has hydrogen bonding as well. Let's see how that affects things. Look at those boiling points. Right around freezing for water. That's a chilly day, and we get this going into the gas phase. And that stuff, it has to be near the 212 Fahrenheit, a really, you know, on the stove, near boiling temperature of water. All has to do with intermolecular forces. Because ether is organic, it is soluble in an organic solvent. Now, low molecular weight ethers are soluble in water. And one of the main reasons is even though a dimethyl ether has no hydrogen that's partially positive to form a intermolecular hydrogen bond with other ethers, it will with water, right? Partially negative, partially positive, and these electrons are partially negative, so that is your hydrogen bond IMF, intermolecular force. And because the water is holding on to the ether a little bit, it can get it to be soluble in water, keep it in the solution phase. But once we get above carbon totals of 5, these become insoluble in water. They just get too nonpolar like. And like dissolves like, but unlike won't dissolve. Okay. So just a quick look at the sort of the trends as the alcohols get bigger and bigger, as the number of carbon atoms that get attached, because they're bigger, even though they all have hydrogen bonding and they're all have dipole-dipole forces. The boiling points get higher just because they're bigger molecules, the dispersion forces are stronger, and it just gets hard to get a bigger thing up into the gas phase. Same process goes on with ethers, but the solubility is in the opposite direction. 4 carbons, alcohols, they kind of dissolve in water, but not very much. And once we add 1 more, it's absolutely will not dissolve. Same sort of thing. Ethers aren't especially soluble in water to begin with. Once we get to 5 carbons, nope, they won't dissolve. All has to do with those, the number of hydrogen bond intermolecular forces that you can form. The more of them you can form, the more soluble you're going to be. Diethyl ether was the first anesthetic by the dentist William Morton. Before that, if you had a tooth problem, there were 2 ways that you dealt with it. 1, quit your whining, live with it. Or the other one is they'd knock you on the head with a big mallet and give you a concussion, knock you out. That's no kidding. That's the way you used to do it. And, you know, if you got on the battlefield in the Civil War, they didn't even have the opportunity to use ether, or they would run out. And yeah, they would knock people on the head basically to get them out whenever they had to amputate a leg or something awful like that. So it's a lot easier now, that's for sure. Now, they don't use diethyl ether very much anymore. There's different reasons for that, but I hope you can see that the main business, no matter what gets attached, is the ether group. And that makes, one of the reasons why it's an anesthetic. All right, just a little bit left having to do with thiols. They're not an especially important functional group as far as commercial products, but they are very important from a biological point of view, so we have to study thiols. Thiols contain an SH group, and it's very similar to an alcohol, right? Same everything. Bent shape, polar, because it's all group 6, just below oxygen on the periodic table, so very much similar in the way physical and chemical properties. And that bent shape is important because even though a Lewis dot structure looks straight, it's not, it's bent. Thiols often have a very foul odor. They stink bad, but not completely useless, as in, ooh, we don't want to make any of those, because there are some cheeses that have a little bit of methane thiol and gives it a certain taste as well as smell. Onions contain 1 propane thiol, and garlic contains 2 propene 1 thiol. And all of these, make some sort of smell, and you can make them actually smell pretty good if you worked at it. And there's ethane thiol is added to natural gas, which is normally odorless, natural gas being CH4, to detect gas leaks. If you've ever been around a furnace, you can always have that little stinky smell, and it's there at parts per million levels. Really, really small amounts of this ethane thiol goes a long way. But if you smell just a little bit, that means there's potential gas leak. If you didn't know it before, you wouldn't know there was a gas leak. The house would fill up with natural gas. You'd light the stove and the whole place would blow up. Now we don't have that issue. So, useful. Naming is very similar to alcohol naming. Parent carbon chain is an alkane. Add a thiol containing the SH group. Number it so that the SH that's attached is the lowest possible number. So we're going to look at that guy, and we're going to say 1, 2, 3. So it's propane thiol that's attached to carbon 1. 1 propane thiol. Here, again, the thiol is attached to carbon 1, so we'll do the naming starting with that number. And since this is a 3-methyl, we got 3-methyl, that's the only substituent attached to this 1 butane thiol. Okay, longest chain with the S thiol group, the smallest number. 1, 2, 3, 4, 5, 6. Hey, you know what? If I went 7, 8, it would be an ethyl group off carbon 6. If I went 7, 8, it would be an ethyl group off carbon 6. So it wouldn't matter. The key here is that there's 8. So it's octane thiol, and it's a 2-octane thiol because the thiol group is on carbon 2, and 6-ethyl because the ethyl group is off carbon 6. Okay, 6-ethyl, 2-octane thiol. Not too bad. Lots of organic compounds contain sulfur other than the ones that we talked about. And disulfides are very important in biological processes. Take two thiols, oxidize them, and you make a disulfide or a sulfur-sulfur bond in between and connect the two. That's a critical factor in protein structure that's called a disulfide bridge, and towards the end of the semester, we will be talking about those. But before that, we can talk about a perm, making straight hair curly. Remember, hair is protein, and so the protein strands normally are linked with a disulfide bond. But the opposite of making disulfide bonds with oxidizing is breaking the sulfur-sulfur bonds and adding H. Notice that we add H and break the bonds. And so the strands aren't long and connected. Instead, they can interlink with oxidizers later, each individual strand, to make them not long and straight, but kinked and curly. So hair is then formed around the curlers, and then oxidizing is applied, and that reforms the disulfide bonds. And it makes it curly. So that's a practical application of doing reactions that affect thiols. Okay, so that's that set. Get working, especially on the reactions part, and do your practice homeworks, and we'll see you next time.